Okay, third and final segment for Chapter 11, Organic Compounds. So we were talking about organic naming and drawing out structures, and now we're going to look at the general properties. So organic compounds, as you may have guessed, are mostly covalent, right? Because it's carbon-carbon bonding with hydrogens, all nonmetals. They're typically going to be nonpolar, except. Now the exception comes in with the things we're about to see, which are going to be your functional groups. So functional groups can lend themselves to some polarity, but carbon chains in general are nonpolar. They typically have low melting points. So for instance, low boiling points, we're going to have gases, think vapors. Gasoline readily turns from a liquid to a vapor. In fact, you can actually see how they change as far as their physical states as the carbon chains grow longer. So as gases, you're talking methane, ethane, propane, butane. Those are all gases, like propane that you use to heat your home. That's a gas. And then butane is the first time you start to see it kind of struggling to either be a liquid or a gas if you look at a lighter. So butane lighters, when you look in them, if you get one of the clear ones, you can see there's a liquid in there, and that's because it's compressed. But the minute you give it some area, as we learned in gases, volume goes up, right? Temperature goes up because they've got to be related. And if the temperature is going up as that volume goes up, that's enough to get the liquid into a gas. Now, as you move further down that chain and make that carbon chain longer, you get straight liquids. For instance, gasoline is octane mainly. And so there we can see readily, though, that it makes a vapor. And of course, because we're talking about gasoline, they're also usually flammable. As the chain grows longer and longer, you slowly go from a liquid to an oil, and then from an oil to a wax, and then from a wax to a solid. And eventually you arrive at plastics. Okay, so that's pretty much the evolution of the carbon chain, going from one carbon out to hundreds of thousands of carbons in a row. They're typically not soluble in water. Okay, so oil and water does not mix. Does that always hold up? Well, not always, because again, we're going to be talking about functional groups. And some of the functional groups we're going to find out are polar, which will make them water soluble. But carbon chains in general are not going to be water soluble. They're more like oil and therefore don't mix with water. Now your functional groups are very similar to substituents, but not quite. And again, the purpose of the functional group is to look at reactivity. Now we're not going to focus on any of the reactions. Our goal here is to be able to look at these functional groups, figure out the pattern, and then see that pattern in other molecules. So that when we look at a generic molecule, we can see the functional groups that are there. So the functions that we're going to be looking for are going to be alkenes and alkynes. Now, notice they sound very much like alkanes. We've converted the A to an E or the A to a Y. And that's actually going to be our double and triple bonds. So A was a single bond. E is going to be a double bond. Y is going to be a triple bond. And I'm going to show you pictures, so don't sweat it just yet. But we'll look at the structure and how the carbons are aligned and what type of bonding we're looking at. Next, we'll have alcohols, which is going to introduce us to oxygen. Single bonded oxygens will be either alcohols or they'll be ethers. Then we can also have a double bonded oxygen. Now, when we have a double bonded oxygen with a carbon, we generate a carbonyl. And the carbonyl can be found in aldehydes, ketones, carboxylic acids, and esters. So we have four functional groups that are going to involve that carbonyl, that CO double bond. After that, we'll look at aromaticity. So what does it mean to be aromatic? And then we're going to end with a couple of nitrogen compounds, amines, and amides. Now, these are not all of the functional groups, and we're not even going to look at all the nitrogen containing functional groups. So we can also get into imidazoles and imines and imines. We're not going to worry about any of those. We're only going to look at amines and amides. All right. If I introduce sulfur, you can get a sulfur series, mercaptans, all kinds of crazy stuff. Same with phosphorus and selenium. So again, we're not going to look at any of those. We're only going to be looking at this little group right here. Now, we're not going to worry about naming, but the nomenclature of the functional group, again, we go back to that IUPAC system. We're basically going to modify the hydrocarbon name to give it an ending based upon the functional group. So here we have alcohols. The minute we have an OH in there, we'll use an OL ending, right? So methanol, ethanol, these are alcohol groups. If we're an aldehyde, we'd end in al, so to be formaldehyde, right? So again, we're not going to worry about nomenclature though, but you'll see these oic acids. So for instance, if you look in your food labels, you'll see benzoic acid is sometimes used as a stabilizer. And that way you can get longevity out of your food. But we're, again, not going to be focusing on the nomenclature. The function, it's just sort of, hey, when we have a functional group, what happens is we change the ending. Now, I want you to treat the functional group just like branches, except when you see them, we're just going to be labeling them. So our functional groups that we're looking for are going to be a specific combination of atoms. Now, the reason, again, is because it's going to give us a known type of behavior. We're going to classify the compound by its functional group. So alkenes and alkynes. Remember I said multiple bonded carbons. So whenever we have a multiple carbon-carbon bond, so here we have the double bond between two carbons, that's going to be an alkene, E-N-E. Okay, so alkene. If we form a triple bond, it's going to be an alkyne, and that's where we're going to get a Y-N-E. So double bond, alkene, triple bond, alkyne. Now notice the angles here. Okay, we're going to be stuck. This is going to be a planar molecule. So this one doesn't look much different than if I were drawing these out, especially if I use those stick figures. But notice this one becomes linear. Again, that's not something you'll need to worry about, but in the drawings, you'll see that. So for instance, remember if we're doing stick figures, because it's a linear compound, it's going to look like that. If it was a double bond, and I guess I kind of have it over there. Sometimes we show the hydrogens on here, sometimes we don't. You can also go like that. Okay, so a couple of different ways to draw it. So we have what's called trans, or we can have cis. Don't worry about the cis or the trans component. You just need to be able to circle that and call that an alkyne, or excuse me, alkene. If it was a triple bond, you just need to circle that and call that the alkyne. So that's all we're asking you to do, is be able to circle that functional group and then label off what it is. And notice here I went through the carbon-carbon bonds. You know, it's just that general representation. Some people want to get very much like, just get the double bond. I'm not going to be that much into detail. I've seen people just put arrows and say that is the alkene, and that works for me. As long as that looks like in your picture, I know what you're saying is the alkene or is the correct functional group, it's going to be fine. All right, so alcohols and ethers, I told you this is going to be the addition of an oxygen. And so here it's going to look like our bases, since we just got done acids, bases a couple chapters ago now, or just the last chapter. There's your base, but in organic chemistry, this is not basic at all, actually. It doesn't come apart. So the carbon-oxygen bond is a very stable bond, and so this doesn't come off. So in order to be a base, that OH group has to be able to dissociate. Remember, that was part of being base. This will not dissociate, so this is not basic. But it isn't what we call an alcohol group. And so we have a carbon-oxygen single bond, and then you have to have the OH for it to be an alcohol. So here's ethanol, that's our drinking alcohol. If I take this hydrogen off, okay, so this hydrogen that's on the alcohol, if I remove that, and we can do that chemically, and replace it with what we call an R group or an alkane. In this case, I just put a methyl over here. So now it goes carbon, oxygen, carbon. That is going to be our our ether. That's going to be our ether. All right. So ether is going to be a carbon-oxygen-carbon bond. And again, these chains could be longer. I have CH3 groups here, but this could easily be another carbon, another carbon, another carbon. This could easily be another carbon, another carbon. Keep going as far as you want. The minute we have an oxygen carbon-carbon situation where we have two single bonds, that's going to be an ether. Now I got ready to say ketone, and that's because that's the next slide. So for ketones, aldehydes and ketones, I've already kind of told you you're going to have this carbonyl, the C double bond O. Now that carbonyl sticks out like a sore thumb whenever you're looking at structures. So when you see it, you can go down that list of 4, possibly 5 things that it could be. Now the first thing it could be is an aldehyde. To be an aldehyde, and you kind of see it's in the name, hydrogen, and we have hyde. So here I have the carbonyl, right? Once I see that I have a hydrogen connected to it, this whole thing with the hydrogen becomes the aldehyde. Aldehyde, there we go. All right, so it's got to have the hydrogen connected directly to the carbon of the carbonyl. So if there's a carbon connected to the carbonyl and another carbon, that's going to give us a ketone. Okay, so the hydrogen has to be connected to the carbon of the carbonyl. If I have two carbons, so that carbonyl is in the middle of a carbon chain, then it's going to be a ketone. And again, just like we saw with the ether, these carbon chains can be as long as they want to be. Okay, as long as it's carbon, carbon, carbon. So as long as you have those three carbons connected, then that carbonyl right there, so this whole thing becomes a ketone. Now, quite honestly, like I said, I'm not going to be a stickler for like the circling on the test. Like a lot of times on the test, it's going to be like this, and you're simply going to tell me what it is. So you're just going to say aldehyde. Okay. You're not going to have to worry about like, circling it or anything like that, especially on a computer test. So with tests on the computer, you pretty much have to look at the structure. You'll see the carbonyl, look at what's connected, and then you're going to literally type in it's a ketone. Okay. If it's a paper test, then I might ask you to circle. As long as you're circling that carbonyl itself and then telling me what functional group it is, that's going to be fine as well. All right, the next two that we have that involve our carbonyl are the carboxylic acids and the esters. So again, the carbonyl is going to stick out like a sore thumb. There it is. And now we have an alcohol connected to our carbonyl. So this is not an alcohol any longer. Now that it's connected to the carbonyl, this whole thing becomes an acid. Okay, and that's actually our vinegar right there. That's our weak acid that we've been studying in a couple of different places. It's also our acetate. So we've seen it in a lot of different functions, and here it is as an organic carboxylic acid. Now we saw previously that we could take the hydrogen off of our alcohol and keep it going, and it would be called an ether. Well, we can do the same thing here. We can pull that hydrogen off. Remember, now it wants to come off. It's a proton, it's an acid, so it wants to come off. We can actually pull that off and keep that chain going with carbon chains, and then it becomes an ester. Okay, so this whole thing now would be an ester. But again, as long as you're circling the carbonyl and then calling it an ester, that's going to be quite all right. All right, so that's it for our carbonyls until we introduce you back to nitrogen. Okay, once we get nitrogen in there, we're going to see we can have an amide as well. But until we get to that, we have a couple more. So we have aromatic, and I'm going to keep this very general. There's actually an equation that goes with aromaticity called Huckel's rule, but we're not going to worry about that. For our purposes, what you're really looking at is the benzene ring. Okay, so it's going to have to be a 6-membered ring, and it's going to have alternating double bonds. So it's going to look like this in pictures. Okay, so you're going to have a 6-membered ring, and then you're going to have double bonds and single bonds alternating around the ring. Now be careful with this, because some of the compounds that we like to use when we're looking at functional groups are called steroids. And steroids have a fused ring system to where we'll have like 6-membered rings that kind of fuse together. And then finally we'll have a 5-membered ring on the end. And that's our stereotypical backbone for a steroid. And then we'll have different functional groups coming off that. And some of them will get tricky because they'll put like a double bond here and a double bond here. Okay, that's not aromatic. It has to be 3 double bonds. It has to be alternating. They can't be next to each other. So physically they cannot be next to each other. So if I have a 6-membered ring and I put a double bond here and a double bond here, that cannot happen. Physically, that carbon has to be linear now, and then you can't make a ring that way. So they have to be alternating, or they can be completely across the ring from each other. But if you don't have 3 of them and they're not alternating, it's not aromatic. All right, so our last 2 are the amines and the amides. If we have an NH2 group, we have an amine. So for instance, it's going to look a lot like the alcohol, except now it's a nitrogen in there instead of an oxygen. And so that would be an amine. Now we can have primary, secondary, and tertiary amines. I don't need you to be able to tell me which one's which, but basically what's going to happen is I'm going to pop this hydrogen off and I'm going to add another carbon. And when we did that before for oxygen, it turned into ether. But for amines, we don't have separate names for those. So it's just an amine, but now it's going to be primary, secondary, tertiary. And it's just going to tell me how many carbons are connected. For us, I just want you to be able to pick out that nitrogen. You see the carbon-nitrogen single bonds, and you know that's an amine. It doesn't really matter if it's primary, secondary, or tertiary. Not something we're going to concern ourselves with. Now, if that nitrogen is connected to a carbonyl, right? So here's our C double bond O, we have our carbonyl, then we have a nitrogen, that's going to be an amide, okay? An amide. So it's the difference in the N versus the D. So amine or an amide. All right, so that's it for our functional groups. Those are the only ones we're going to concern ourselves with. That takes care of oxygen. Most of the nitrogens that you're going to see when you're in AMP 1 and 2 and going into the medicinal worlds. If you really want to brush up and know more functional groups, then you might want to look at sulfur as a functional group as well. A lot of drugs have sulfurs in them. They have the whole sulfa drug lines like penicillin and things of that nature. Again, that's totally up to you. None of that will be on your test. But if you have questions about any of it, feel free to give me a call or an email or a text. To review then, what do you need to be able to pull out of this chapter from these three segments? Well, you need to be able to name, and you're only responsible for the first carbon, 10 carbons, right? So you need to be able to name those. And notice we didn't do any structures where I drew the structure from the name, but you do need to be able to do that. I find that students who are able to take the names and turn them into structures, it's usually easy to do if you can take the structure and turn it into a name. So the harder of those two is what we actually did together in this videos. So you need to be able to take a structure and then draw its name from that. But on the exam, you will also be given names and asked to draw the structure. Okay, so make sure you practice that. There's a lab that's attached to this week's lessons. Make sure you look through that lab. It's a dry lab. And again, it's going to help you practice your drawing, both condensed and expanded formats. The only other thing you have to be able to do out of this chapter is pick out those functional groups. And again, only the functional groups that we just went over. So while there may be other functional groups out there, those are not ones you need to concern yourself with. Also, under your folder for practice, I will put a couple of, I think it's just one word file actually, that's going to give you a list of compounds where you can practice picking out these functional groups. And typically on your exam, that's the list I pull from, but it'll be real world things. So, real compounds that are in your everyday world. So that way you can see that organic chemistry is around and that kind of stuff. All right, so hopefully that concludes chapter 10, and if you have questions, you'll get a hold of me. So don't make yourself a stranger, come to a study session or make an appointment. Okay, talk to you soon.